In the realm of ride-hailing platforms, achieving long-term fairness is a complex challenge. Existing studies often fall short due to their focus on short-term decision-making and traditional optimization methods. This paper proposes a novel approach to address these limitations, introducing a dynamic Markov decision process model. The proposed model comprises two key components: a prediction module that forecasts future requests and a customized scalarisation function for multi-objective multi-agent queue learning. This innovative approach aims to balance efficiency and fairness in ride-hailing services. The authors conduct extensive experiments on a real-world dataset, comparing their proposed method against existing state-of-the-art methods. The results demonstrate the superiority of the proposed method, highlighting its potential to significantly improve the fairness and efficiency of ride-hailing platforms. This research contributes to the ongoing efforts to optimize ride-hailing services, emphasizing the importance of considering long-term fairness in decision-making processes. By leveraging advanced machine learning techniques and dynamic modeling, this study paves the way for more equitable and efficient ride-hailing systems. The current approaches to creating equitable ride-hailing systems, relying on heuristic or linear programming, are inadequate in providing non-myopic solutions. These traditional algorithms focus on immediate future trends without considering historical discrepancies or future demand patterns. The Markov Decision Process, MDP, proposed by Raman et al., is a step towards balancing efficiency and fairness, but it only considers historical patterns for raised requests, neglecting future conditions. A scenario illustrated in Fig. 1 demonstrates how an emphasis on short-term equity can lead to long-term inequitable allocation plans. Drive's primary concern with weekly earnings underscores the need for a more comprehensive approach that addresses short sight, concept drift, and disparity between utility and fairness increase across time. Long-term fairness in ride-hailing platforms is a concept that has been largely overlooked in previous studies, which primarily focused on improving fairness for the driver with the lowest utility. However, this approach fails to consider overall fairness among all drivers and the challenge of balancing utility and fairness over a long time horizon, where variance inevitably increases. To address this limitation, the authors propose a Markov Decision Process, MDP, based method that leverages historical data and forecasts to achieve long-term fairness while balancing total utilities for drivers. This approach aims to reconcile the objectives of utility and fairness in ride-hailing systems. The proposed MDP-based method utilizes dynamic programming to optimize the allocation of rides to drivers based on their historical performance and current demand. By considering both short-term and long-term allocation strategies, the authors aim to minimize the disparity between these two approaches and ensure that all drivers receive a fair share of rides over time. Key to this approach is the use of historical data and forecasts to inform decision-making. By analyzing past ride patterns and demand trends, the MDP-based method can predict future demand and adjust ride allocations accordingly. This not only helps to ensure long-term fairness but also improves the overall efficiency of the ride-hailing platform. In conclusion, the study highlights the importance of considering long-term fairness in ride-hailing platforms and proposes an innovative MDP-based method to achieve this goal. By balancing utility and fairness among all drivers, this approach has the potential to improve the overall performance and sustainability of ride-hailing systems. In the realm of ride-hailing systems, long-term fairness remains a pressing concern, as drivers' earnings often fluctuate greatly over time. To address this issue, this research proposes a novel approach leveraging a Markov Decision Process, MDP, based model. This innovative framework considers diverse data patterns to mitigate unfairness, integrating a time series forecasting module to predict future ride requests. By doing so, the model endeavors to preserve utilities while minimizing the disparity in earnings among drivers. The MDP model's core objective is to optimize the allocation of ride requests, ensuring that drivers' earnings converge over a broader time horizon. This is achieved by incorporating a forecasting module that accurately predicts future demand, enabling the model to make informed decisions about ride assignments. The proposed methodology is validated through rigorous experiments utilizing a real-world dataset, which demonstrates improved performance compared to existing methods. The results show that the MDP-BASED approach effectively reduces earnings disparity among drivers, promoting long-term fairness in ride-hailing systems. The integration of time series forecasting enables the model to adapt to changing demand patterns, ensuring that drivers' utilities are preserved. This research contributes significantly to the development of fairer ride-hailing systems, providing a novel solution to a long-standing problem in the industry. In the context of ride-hailing platforms, a balance between fairness and utility is crucial. Studies have shown that prioritizing fairness without considering utility can lead to no earnings for drivers. The problem of long-term fairness in ride-hailing is formulated as a directed graph where nodes signify locations and edges represent travel distances between these locations. Each driver's state at a given time is described by their vehicle capacity, number of riders, geographical location, and total utilities gained from assigned requests. The time length of the problem is divided into 3 parts: historical orders, current orders, and future orders. The utility of each request is calculated based on the geographical distance between the start and end locations of the request and the distance from the driver's current location to the start location of the request. This calculation reflects the balance between profit and cost and is performed at the moment a request is assigned. It is assumed that drivers choose the shortest possible route. The optimization of driver assignment for ride-sharing services is a key aspect of this research, focusing on requests prediction, overall efficiency, and long-term fairness. Historical data is analyzed to predict future requests, aiming to maximize the total utility acquired across all drivers. Efficiency is defined as the total utility, while long-term fairness is calculated as the variance of utilities among drivers. The authors propose a method utilizing equations 1 and 2 to optimize the assignment, balancing driver and rider needs. Optimizing ride-hailing platforms is crucial to achieve long-term fairness among drivers while maximizing total utility. To this end, a mathematical model is proposed, where the objective function balances fairness and total utility with a weight parameter, lambda. The problem is subject to constraints ensuring each vehicle is assigned no more than one request. A novel solution is introduced using a multi-objective multi-agent reinforcement learning (MOMARL) algorithm, which considers real-world dynamics, initial conditions, fairness, and equity. This approach enables different drivers to learn distinct agent behaviors based on their starting locations, optimizing total income while promoting fairness. A central controller acknowledges the status of all agents, ensuring allocation decisions consider the collective situation of all drivers. This promotes a fair distribution of utility and opportunities across the network. The scalarisation function in MOMARL balances utility and fairness, aiming for Pareto optimality. To adapt to future request patterns, a time series prediction module is integrated, allowing online adaptation to changing demand. This approach addresses the limitations of current ride-hailing platforms by incorporating fairness considerations into the optimization process, leading to a more equitable distribution of opportunities and income among drivers. By leveraging MOMARL, the proposed model can optimize ride-hailing platforms for long-term fairness and maximum utility, providing a more sustainable and equitable experience for drivers. In ride-hailing systems, achieving long-term fairness is a complex challenge. To address this, a novel model is proposed, combining time series prediction, multi-objective reinforcement learning, and a scalarisation function. This integrated approach operates in 4 stages. First, a time series forecasting module predicts future requests based on historical data. This prediction informs the allocation plan, which is optimized through multi-objective multi-agent Q-learning. This optimization balances competing objectives, including efficiency and fairness. The scalarisation function plays a crucial role in achieving this balance, ensuring that the system prioritizes fairness while maintaining efficiency. In the third stage, requests are assigned to drivers based on the optimized allocation plan. Finally, the model learns from the outcomes, adapting to changing system dynamics and driver behavior. By integrating these components, the model aims to maximize utilities among drivers while ensuring geographical fairness. This approach has the potential to promote a more equitable and sustainable ride-hailing ecosystem. In the pursuit of long-term fairness in ride-hailing platforms, A molecule-based model is proposed, which involves finding the shortest path for each request and assigning drivers based on efficiency and fairness. This model learns from matching results to optimize both efficiency and fairness, aiming for Pareto optimality. A time series forecasting module, utilizing a multi-layer perceptron (MLP), predicts future requests based on past data. This prediction is integrated into the multi-objective multi-agent queue learning framework, which formulates the ride-hailing assignment problem as a Markov decision process. This enables strategic assignment of incoming ride requests to available drivers, considering both immediate demands and predicted future conditions. By leveraging this framework, the model can balance the trade-off between efficiency and fairness, ensuring that drivers are assigned to requests in a way that maximizes overall system performance while minimizing disparities. The molecule-based approach demonstrates a novel solution to the complex ride-hailing assignment problem, offering a promising direction for improving fairness and efficiency in ride-hailing platforms. In multi-agent systems, the proposed model employs centralized multi-objective multi-agent queue learning (MOMAQL) to balance utility and fairness in ride-sharing platforms. By incorporating historical, current, and predicted future requests into the action space, the model can be trained on future request patterns. A scalarisation function is designed to balance utility and fairness while maximizing the objective, reducing the dimensionality of the multi-objective environment to a single scalar dimension. This facilitates the balancing of utility and fairness over a long time horizon, as these objectives increase at different speeds. The reward function for each agent, or driver, is calculated as the sum of geographical distances between the starting location of an assigned request, the ending location of the assigned request, and the agent's current location. This encourages the balance between utility and fairness by considering the geographical distribution of requests and agent locations. A centralized controller queries raised requests and assigns them to different agents based on their current locations, simplifying the problem by assuming drivers always accept requests without cancellation. The scalarisation function plays a crucial role in balancing utility and fairness, as these objectives increase at different speeds, making it challenging to maintain a balance between them. By leveraging MOMAQL, the model can effectively navigate this trade-off, providing a valuable solution for ride-sharing platforms seeking to optimize both utility and fairness. The authors evaluate their proposed method for achieving long-term fairness in ride-hailing platforms, comparing it to several baseline methods. The results, presented in Table 1, demonstrate that the proposed method outperforms the baselines, achieving the highest total utility and lowest normalized fairness. A scalarisation function, SRM, is introduced to combine utility and fairness objectives. This function, defined in equation 7, incorporates two key parameters: lambda, the weight for fairness among different drivers, and omega, the scale to adjust fairness into the same range as utility. By adjusting omega, the weight assigned to fairness is adjusted to prevent fairness from dominating the objective function as the time horizon increases. Figure 4 illustrates the performance of the baselines and the proposed method in terms of fairness as the time horizon increases. The results show that the proposed method consistently outperforms the baselines in terms of fairness, even as the time horizon increases. The authors utilize the New York City taxi dataset, a publicly available dataset containing essential information on all requests, to evaluate the performance of the proposed method and baselines. The scalarisation function SRM is designed to balance utility and fairness objectives, with the weight lambda controlling the trade-off between the two. By adjusting omega, the authors can adjust the weight assigned to fairness, ensuring that it does not dominate the objective function as the time horizon increases. The experimental results demonstrate the effectiveness of the proposed method in achieving long-term fairness in ride-hailing platforms. The authors utilize a dataset of taxi requests executed in Manhattan between March 1, 2016, and April 1, 2016, where each request includes the pickup and drop-off locations recorded in longitude and latitude coordinates. The shortest travel time between pickup and drop-off locations is recalculated as the mean travel time across the time period, and multiple locations are merged as a node in the constructed graph. It is assumed that drivers always choose the shortest path to complete a request. The authors select 4 baselines for comparison: greedy, reassign, laugh, and balance ride pooling. Greedy is implemented with the objective of balancing efficiency and fairness according to equation 3. Reassign, laugh, and balance ride pooling are existing fair ride-hailing methods that are modified to use the fairness definition according to equation 2. In the experimental settings, data before March 26, 2016, is used as training data, and the requests from March 26, 2016, to April 1, 2016, are predicted. To reduce training time, peak 2-hour data is extracted and used for request prediction output. The first 7 days of data and the extracted output from time series forecasting are used to train the proposed model, and the remaining data is used for testing. A stratified sampling method with a sampling rate of 0.05 is used for the training data. The parameters lambda, omega, and gamma are set to 1, 0.6, and 0.9, respectively, to indicate no preference on utility or fairness, scale utility and fairness into the same range, and as the discount factor. In the pursuit of long-term fairness in ride-hailing platforms, experimental results are analyzed to compare the proposed method with baseline approaches. Normalized fairness is defined as the normalized standard deviation among utilities for different drivers, calculated using equation 8, which represents the mean utility across all drivers. Results, summarized in Table 1 in Fig. 4, demonstrate the proposed method's superiority in balancing efficiency and fairness, even outperforming traditional optimization methods on a real-world dataset. The findings underscore the significance of considering future patterns in ride requests to improve utility, thereby ensuring the stability of long-term fairness across varying time horizons. By optimizing for fairness, the proposed method achieves a more equitable distribution of utilities among drivers, ultimately contributing to a more sustainable ride-hailing ecosystem. The experimental results provide a comprehensive evaluation of the proposed method's performance, highlighting its ability to adapt to dynamic ride-hailing environments while maintaining fairness. The study's insights have significant implications for the development of more equitable ride-hailing platforms, emphasizing the importance of incorporating fairness considerations into optimization frameworks. The analysis on the proposed method's performance in terms of fairness and total utility is comprehensive, comparing it with other methods and variations. The authors compare the proposed method with balance ride pooling and reassign, highlighting the stability of fairness in reinforcement learning-based methods as the time horizon increases. This is crucial for drivers concerned about equity in profits over the long term. An ablation study evaluates the request prediction module's influence on balancing total utility and fairness. Table 2 illustrates the performance comparison, showing that the proposed method without fairness achieves the highest total utility but poor fairness. By incorporating fairness, the proposed method promotes fairer earnings and increases total utility. The mean squared error of the request prediction module is 94.69. Contributing to the improvement in total utility and fairness through predicted future requests in the training process. The stability of fairness with increasing time horizons is also investigated. Figure 5 shows the proposed method without fairness exhibits unstable fairness due to the lack of fairness consideration, while the proposed method and the method without prediction demonstrate improved stability and fairness as the time horizon increases, indicating the effectiveness of the request prediction module in enhancing fairness stability among drivers. The paper discusses the concept of long-term fairness in ride-hailing platforms, focusing on achieving stable and higher fairness over longer time horizons. It argues that taxi drivers are more concerned about long-term earnings. To achieve this goal, the authors introduce a request prediction module before allocation, allowing for look-ahead windows in the proposed allocation system and eliminating the assumption that requests always follow the same pattern. They exploit the output as part of the action space for the allocation model, designed using multi-objective multi-agent Q-learning. The experiments conducted on real-world data demonstrate the effectiveness of the proposed method in maintaining overall fairness in the longer time horizon and enhancing the stability of fairness when the time horizon gradually increases. The results show that the prediction module achieves fairer results when the length of the time horizon is 1 and 2, and as the length of the time horizon increases to 3 or more, the fairness of the proposed method is better than the proposed method without prediction and more stable. The paper concludes by highlighting the importance of long-term fare earning for taxi drivers and the effectiveness of the proposed method in achieving this target. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have.